Wi-Fi code. Okay, it is 123.04237.
Thank you very much. Thank you to the organizers for the invitation. It's nice to be back in Durban. So I was asked to give 2 lectures on the SYK model and the supersymmetric SYK model. So I want to essentially introduce the model in the first part, and then in the second part we'll talk about some analog of the SYK model to 2 dimensions, so 1 plus 1 dimension. By way of an outline, so today I think I'll spend most of the time talking about the SYK model, and I'll draw quite heavily on Robert's very nice lecture at one of these schools a couple of years ago, maybe, and also talks by Dr. Stanford that were given at the KITP, as well as Kitao's original lectures at the KITP in San Barbara. And then I want to essentially move toward generalizing this idea to 1 plus 1 dimensions. So we'll take another look at the SYK model from this perspective, and this will follow the work of Stanford and Mandelstam, and then some work that I did with Stanford and everybody, trying to extend this SYK model to higher dimensions. So the third and final part, if I get to it, will be focused on that analog model in 1 plus 1 dimension, which is really a model of random, disordered sort of conformal field theory, in which we try to construct an SYK analog in high dimensions and try to extract some of the physics from it. A lot of what I'm going to say is fairly general. So it applies to 0 plus 1 dimensions, 1 plus 1 dimensions, supersymmetric, non-supersymmetric. I'll try and get the formalism going in as pedagogical a way as possible, which is another way of saying I might not get to where I'm going. But we'll start and we'll see how far we can go. So the first part, I want to go through fairly quickly, and I'm not going to give much in the way of too much detail. You can find them in Robert's lecture or Google any one of the many talks that Dr. Stanford's given on the topic. As David just told me this morning, conferences are not usually a good place to learn how to compute things. So I'll give you the essence of what the SYK model is, and then we'll move on from there. All right. So if you don't know by now, the SYK model is a many-body Hamiltonian with n sites in 0 plus 1 dimension. So it's a quantum mechanics problem. Can everybody read from the back here? Okay. Right, bigger. At each of the sites, there is a Majorana fermion. Like this. That satisfy perfect algebra, psi I, psi j, delta ij, at I, j, go from 1 to n. And this will be important as we go along, that these guys in 0 plus 1 dimensions have mass dimension 0. And the structure of the Clifford algebra is such that when I is not equal to j, these guys anti-commute. When I equals j, psi I squared is just a half. So the Hamiltonian for this model has the following structure. So H is sum over, say, J, K, L, and M of some set of couplings, J, K, L, M, normalization, I think we 1/4 factorial, psi, J, psi, K, L, M. And because these guys have satisfied the Clifford algebra, the J's have the property that it's got to be anti-symmetric in all of the indices. And so it's, let's say, completely anti-symmetric. And the model is an all-to-all interacting model. So with all the fermions interact with all the other fermions. These guys, the J's, have mass dimension equal to -1. And so they're relevant. And since the coupling is relevant, the theory is strongly coupled in the infrared and weakly coupled in the ultraviolet. Now, what makes the SYK model special is that these couplings are a set of random time-independent variables. The fact that they're random means that we have a disordered system, and the fact that they're time-independent tells us that this is a special type of disorder called quenched disorder, as opposed to another type of disorder which condensed matter people deal with called annealed disorder. It's a question of how you take your averages over this. So this is, the SYK model is a
Sorry,
yeah.
maybe a stupid question. So by random we mean there is this family of Hamiltonians parameterized by J,
Yeah.
and then you pick a random J and you try to study how this family of Hamiltonians behave.
Correct. And the point is, you can think of it as doing a bunch of different experiments, and for each experiment you sample the J from a particular distribution. We'll pick the distribution to be Gaussian, say, because we can do all the integrals. But for each of them, it's a fixed J. So J has the property that it's, let me note that actually. So J has the following properties. One, it's random. Two, it's time independent. Random means we have a disordered system. Time independent means the disorder is quenched. And three, we sample J from some distribution. So we'll take J to be sampled from a Gaussian distribution with zero mean and some variance. So the variance is 1/3 factorial, it's normalization. So J I, J, K, L, J, M, and P is either j squared over n cubed. If MNOP is an even permutation of IJKL, or sorry, or 0 otherwise. So all in all, we'll say that the SYK Hamiltonian is a 4-body Hamiltonian with quenched disorder. So right. So,
Sorry.
Yeah.
So is Gaussian in the separation of the indices, ij, kl? Is Gaussian in what parameter?
it's Gaussian in the sense that I let me write down the distribution that we pull this guy from and then we'll talk about. So okay, so P of J, K, L, M is exponential minus n cubed over 12 j squared j I j k l j I j k l with some normalization on front. Okay. Very good. So the point here is that we want to be able to compute things from this model. In particular, we'd like to write down what its spectrum is. So we need to be able to compute correlation functions out of this. So from the Hamiltonian, we can write down the corresponding Lagrangian. So that's just a half psi, let's say j psi j dot minus j k l m over 4 factorial psi j k l m. This is the free part and all the interaction is contained here. So we can immediately compute the free 2-point function, the free Green's function for this. Let's call it G naught. This thing satisfies the following. If I take the integral over all fermions, e to the minus s naught, where s naught is the integral time of L naught. Psi I of t, psi j of naught, I'll get delta I j, t naught of t. And we can calculate what this integral is. If you do so, solve for g naught, you find that g naught is half times the sine SYGN of T. Okay, so we have the free Green's function for the theory. So we'd like to use this to calculate the time-ordered two-point correlation function. Again, we're trying to build out the spectrum for the theory, so correlation function is really what we want to calculate. And again, I don't want to go through the details of this calculation. Robert does so very nicely, capturing a lot of the combinatorics of how to do the width contractions and things like that in his lectures, and I'll refer you to there. I want to get the essence of this and show you how we can think about the correlation functions again in a slightly different way. All right, so we want to calculate the two-point function time-ordered two-point function T of psi I T1 psi j T2. And T is, as usual, the time ordering operator, and this thing is the integral of psi k e to the minus s psi I T1 psi j T2. And let me emphasize that this is now the full action. This is the action for the full interacting period. As opposed to this, which is the action for the free quantum. Okay. So you can evaluate this by Taylor expansion and computing each term by term, and then identifying what the Feynman diagrams are that correspond to each term, doing the width contractions, and then calculating in a systematic way all the terms.
Although here J is not the small, or is it the small?
No, it's not. But we're going to be interested in the large n limit of this. But what I want to emphasize here is the following: that once you do all of that, you find that the diagrammatic expansion has a particular form. And this form is important for a couple of reasons. One of which is that basically just identifying this form of the dominant Feynman diagrams and the perturbative expansion of the theory is what led Whitman to join the dots between the large n limit of this theory to random tensor models, okay, which is in some sense some kind of sweet spot between matrix models and vector models. So I'm appreciating that a very particular class of Feynman diagrams dominates the perturbative expansion of this theory at large n is important. So again, I would refer you to Robert's lecture of the same series of schools. It is the same series, right? Yeah, roughly speaking. Okay, the same series of schools a couple of years ago, in which he derives this in a very precise way. I'm just going to write down the large n by n I mean this n, the large n the rotation series is dominated by Feynman diagrams of the what's called, or what's uncalled melodic form, because they look like melons, I guess. So the diagrammatic structure is like this. Here's your Green's function. Plus other terms of the same form. There are a bunch of other diagrams, but there's a large n suppressed. Okay, so these are the diagrams that dominate the Feynman the perturbation series at large n. And the dotted line here denotes the disorder average. And the point here is that all of the disorder averages have to be taken on the same sunset diagram. Okay? So you expand, to summarize, you expand this exponential, expand the integral, term by term, evaluate them, you see which diagrams dominate in the large n, and you find that these are the diagrams that dominate the series. So this is important. This tells us that the SYK model has a very particular large n structure. Now, in order to solve the theory of large n, what we need to do is to sum all these diagrams. And we can do that, fortunately, at least. Okay, so we can do that, and we can solve the resulting equation, which is called the Schwinger-Dyson equation, in a particular limit. So this is what we're going to do. We're going to explore which limit Schwinger-Dyson equation that results in this summation of the diagrams can be solved. So we want to solve the large n theory by summing these diagrams. So let's talk a little bit about this. We're not going to justify term by term how to do that, but what we will do is write down the Schwinger-Dyson equation. And then talk about its various limits. So the point is, when you sum these diagrams, the Green's function, the full Green's function, this guy, solves a particular integral equation called the Schwinger-Dyson equation. So let's write down the Schwinger-Dyson equation. And the way you would check this is to check term by term that each term in the Schwinger-Dyson equation recursively generates the full perturbation series.
Sorry, so before that, could you explain a bit more what the dotted means?
Okay.
It's like to me there's an extra interaction going on and it goes quintic, but actually it's quantic.
Okay, so in each diagram, so this is the usual 4-point interaction at each vertex here, right? But then I have to, the disorder average, I have to take a disorder average over this. And the disorder average involves me contracting some additional indices that come from the J's. So each of those dotted lines corresponds to the disorder average that I'm taking. Okay. So let me, I'll show you explicitly how this, how to take the disorder average a little later if you want.
So, sorry, but this idea that we are not interested in a specific JI, JKL, but on like the sum of...
Exactly.
a lot of them divided by the number.
Correct.
So it's like randomized.
That's right.
And we do that diagram by diagram.
Exactly. Exactly. Okay. Good. Okay, so let me call this guy delta ij g of t1 minus t2. And the point is that this Green's function now satisfies this Schwinger-Dyson equation. G of t1 minus t2 is g naught t1 minus t2 plus j squared integral of dt prime g naught t1 minus t g of t minus t prime cubed t prime minus t2. So this is an integral equation that the two-point function satisfies, and you can show by starting off with a free Green's function and then plugging in and then solving that and plugging in and solving it, that it recursively generates the same perturbation series that we have on this side. Okay. The point is that if you yeah.
Are those integrals over infinity, or are they bounded between t1 and t2?
They're bounded between t1 and t2. Yeah. So usually one casts this into a slightly different form by taking j squared times g of t minus t prime cubed to be the fermion self-interaction. And then in terms of this reads g naught of t1.
So if again this is ij, I suppose it's canonical the way to put them, so there's no way to specify.
I'm sorry, say that again.
So if this is ij, that the one function can be.
Delta ij.
I mean, I suppose that delta ij, there is no kind of quantitative function on the terms which are with the kind of.
Oh, no.
No, so it's no way of.
Plus integral dt prime g naught of t1 minus t sigma of t minus t prime g of t prime minus t2. So this is the fermion self-interaction. The point is to then solve the theory.
Yes. G naught, the last term, I guess. After the fermion self-interaction, the one following is the free. Sorry, no, it's the one is version. So G naught, then sigma fermion self-interaction, and then G of G naught.
No G.
G.
Yeah. Okay. So the point is to solve the theory, I have to solve this integral equation, which we can't do exactly, but we can do in certain limits. One limit that we can do it in is the infrared limit. Because of the fact that the coupling is relevant, the infrared limit here means sending J to be very large. Okay? So if I take J to be very large, if I send J to infinity, then in this limit we can solve the Schwinger-Dyson equation. And in this limit, this equation reads that 0 is g naught of t1 minus t2 plus the integral of t of g naught t1 minus t integral over dt prime self-energy t minus t prime g t prime minus t2. And the structure of this equation tells us that this guy must be minus delta of t minus t2 for this two. So now I have equations for sigma and for g. We can solve that in this method. Their solution is not particularly important in this case, but I do want to make one mention that the variables g and sigma are usually taken to be collective variables to recast the theory in the language of collective field theory. Okay? So this is important because it gives us an effective description of the theory in this limit.
Sorry, should that be obvious? Maybe I am missing something. So first, from the first line to the second line, we have missed j squared. So j squared is somewhere inside sigma.
Yes?
And then,
So j squared, so sigma is j squared this guy.
right, and then you take that to be very large.
Yep. And then g goes to 0. Okay. And so I get this equation. So in order for this to be true, this has to be this. That gives me an equation for this, plus the other one gives me,
Sorry, and the fact that j goes to 0 is easy to see.
the fact that g goes to 0.
Yeah.
Well, it's supposed to decay.
Right.
So
So
the
in the case,
variety-
I 1 over j to the dimension.
That's right.
Good.
Okay.
With the dimension of psi, which is positive.
Correct.
Yeah.
Yeah. Okay, so very good. So there are several important properties that the SYK model has. One of which is that it has an emergent conformal symmetry in this infrared element. And the reason for that is because if we start off from the Schwinger-Dyson equation and rescale time to some function f of t, then the following is true. G of t minus t prime will go to df by dt df t prime by dt prime to that quarter g of f of t minus f of t prime, and sigma t minus t prime goes to df dt df dt prime 3/4 sigma of f minus f prime, sorry, f t prime. So the factor of 3 comes from the fact that we take 3 factors of g in the definition of sigma. Together, Okay, good. So, the way G and sigma scale, when we rescale the time variable, tells us that there's an emergent conformal symmetry in the item. Okay. Let me see. Write down features that we're going to use in what follows.
Could you explain why this is emergent conformal symmetry? This thing, or why this implies?
Because in general, I can't solve the string elastic equation. Right? I can solve it in this particular limit. In this particular limit, when I solve it, I find expressions for G and sigma. And the expressions for G and sigma are conformally invariant only in this limit when J goes to infinity.
Yeah, so if you take a two-point function, for instance, and you look at the word identities for conformal transformations, and there are change of coordinates that takes f t to f of t, the rules are that the two-point function is multiplied by these factors of the f dt.
That's right. That's right. So in 0 plus 1 dimensions, the conformal group is PSL R this restriction.
And from this 1/4 and 3/4, we can read off the dimensions of.
Exactly.
No, but that kind of follows from just dimension analysis of GQ times G and the two integrals of T. That needs to have dimension.
But the
Two
dimensional analysis is,
GQ.
is okay in the free theory, no? Yeah, we are going to the deep infrared.
No, but that's exactly the point. In the deep infrared, you assume that G has some dimension, and the dimension of sigma has to be 3 times the dimension of G. And the double integral needs to be a number, so that's dimension 0. So the dimension of G and has to be 1/4. Sorry, 2/4 in some sense, because you have two integrals of T. So.
Maybe I can comment. Since if you think of a space of theories, you value step large n and you go to an infinite critical point, and you have scaling variance. This is a unique example where you will also see this generalization. So it's not, scaling variant points are typical. So the huge space of theories will not have this property.
Right.
So,
That's right.
so just by scaling, that applies to many theories.
Absolutely.
But this is very unique. So
Yeah.
we should appreciate that it's not that often.
Yeah, it's not just for scaling transformation.
No,
It's just
no.
for general transformation.
This is
So
very
it goes well
unique.
beyond the
It's very unique, and I only know this example.
Very
Many theories that I have.
So let me summarize some of the salient properties of the SYK model. So again, these are the salient properties that we're going to need, that we're going to look for if we try to generalize the model. Right? These are, like Antonio said, it's a very special theory. So if we're going to try and extend it in any given way, supersymmetric, high dimensional, supersymmetric, whatever, it had better retain these nice properties that we've identified, or that I'll write down now, of the SYK quantum mechanics. So, first one is that in the IR, so this is where J squared is very large. The 2-point function, the full 2-point function, g, let's say of tau, goes like sine of tau over 1 tau to the half. And the scaling dimension of all the fermions is 1/4. In the ultraviolet, the theory is free, since in this limit J squared is much less than 1. G of tau goes like sine of tau, and the scaling dimension of the fermions is 0. Okay. So we've noted already that there's an emergent conformal symmetry in the infrared. But the theory also has the remarkable property that it is chaotic. But not just chaotic, it's maximally chaotic in the sense that there's a very generic bound on the chaos exponent, or the Lyapunov exponent. And the SYK model saturates that bound. It's one of a very small number of theories that do so. So the theory is chaotic. So let's say it's maximally okay. So there's this thing called the Molosino-Schenker-Stanford bound, which tells us that the Lyapunov exponent, which measures essentially, okay, so this is the quantum version of the classical Lyapunov exponent, where if you take let me take a classical problem and just pause it, and then I want to come back to this, so I don't want to spend too much time now talking about it. So this is the problem of Silent billiards. Okay, so you take a box, you put an obstruction in the box. So let's say we take a spherical ball and we put it in the box, and then we take a particle and we bounce it off the box. So we start off with something like this. And we watch it bounce. And then we start the particle again with a slightly different initial condition. So now imagine we take the particle and we start it off slightly different. So in this case, very small variation results in an exponentially divergent trajectory for the particle in a chaotic system. So this is the problem of chaotic values. And how big this divergence is measured by the exponent in the so if I calculate dx of t by dx of naught, so this is the change of the trajectory of the particle with respect to its initial condition, you'll find that it goes like e to the lambda L, the classical Lyapunov exponent, times t. Okay, so this is called the Lyapunov exponent. It's a measure of how chaotic the system is. The question is, how do you calculate that in a quantum system? And the answer is by studying 4-point functions of the theory. Actually, you're studying a particular commutator in the theory, and you want to show that for generic operators in the theory, this particular square of a commutator, the expectation value of the square of this commutator, exhibits a similar property. And then you can massage this a little bit for a class of operators and show that this is the same as measuring a certain class of 4-point functions. They're not the traditional 4-point functions, they're what's called out-of-time ordered correlation functions, in the sense that you don't order your operators in increasing time from right to left. And we'll come back to that in a little bit once we understand how to compute 4-point functions. Okay. So what we're going to do, so this is a remarkable property of the theory in that it's not only a chaotic system, it's maximally chaotic. It's as chaotic as it's going to be because this bound is saturated in the SYK system. Okay. So this is a clue as to what to look for in a dual gravitational system to SYK. Okay.
What is beta?
1 of t.
That's usually by beta inverse, right?
Yes, you're right.
So you put all the system in some finite temperature.
Correct.
Somehow.
That's right.
So you make the dimension common.
Okay, so the operator growth. Okay. I have until 10:30, yes?
Yep.
Okay. Very good. So this, roughly speaking, captures the kinds of things that we would like to see in any theory that exhibits what we will call SYK physics. My notes have a lot more detail than I'm writing down on the board, so, and I'm happy to make that available to anybody who wants it. I guess I can give it to you guys.
Fantastic. I'll stick on the website. Thanks for that.
Yeah, a mess.
Okay. So, okay. All right, yeah. So the question that I'd like to ask right now is, having set out all of this stuff with the SYK model in 0 plus 1 dimensions, can we extend this to say 1 plus 1 dimensions and then hope to deal with the conformal field theory, where we have a whole lot of tools to deal with conformal field theories that we could bring to bear on the problem? Maybe we'd learn how to compute 4-point functions, maybe in the Zamolodchikov sense we could solve the theory completely. Right? So can we extend this model to higher dimensions and retain the same SYK type of physics? So this was the question that we set about trying to answer. So there's several approaches to extending the model to higher dimensions, and these were taken by a number of different groups. So the first one is what I would call discrete high-dimensional SYK models. So this is what you would call a chain of such SYK models. So this model takes place at a point. It's a Hahn mechanics problem, 0 plus 1 dimensions. Okay? Take a whole bunch of these points and link them together, and then join the J's in a particular way, so you have interactions between each of these guys, and you get a chain of such SYK models. So this was originally proposed by Gu, Shi, and Stanford. It has the property that it's a one-dimensional model, 1 plus 1 dimensional model, but it's a discrete 1 plus 1 dimensional model. We would like to look for some continuum 1 plus 1 dimensional model, so we can treat it with the conformal field theory techniques that we would like to. Another option involves the introduction of non-standard kinetic terms. And one such model was introduced by Turiachi and Berlinde. So this is a theory that has not the usual kinetic term for the fermions, and it has some interaction. And what you want to show is that in a particular limit, the interaction term dominates, so you don't worry about this non-standard kinetic term. But again, at some point you have to deal with that. And so we would like to not do that, so we'd like to propose a standard d phi squared or d psi squared kinetic term. The third model, third class of models, let's say a third model, was introduced by the Coos and collaborators. This was a random theorem model. So this has a standard kinetic term. It's a Dirac type kinetic term with some 4 Fermi interaction. But you make the 4 Fermi interaction random. So this is a Turing model of sorts, except because of the random interaction, it's called a random Turing model. And this has other issues. Okay, so let me just talk about some of the issues with extending to 2 dimensions. Well, in 1 dimension, as we've already said, a fermion has mass dimension 0. So the 4 Fermi interaction that the SYK model had is a relevant interaction. And in the infrared, the theory flows to some strongly interacting SYK type things. This is something that we'd like to preserve. Well, the problem is, in 2 dimensions, a fermion, a canonical Dirac kinetic term, has mass dimension 1/2. So this says that a 4 Fermi interaction has 4 times 1/2 is 2. That makes the interaction marginal in 2 dimensions. And in fact, everything that I said for the SYK model had a 4 Fermi interaction. But there's nothing stopping us from increasing the order of the interaction. And in fact, Mandelstam and Stanford did exactly this. They considered a Q Fermi interacting system and derived everything that they were talking about for general Q. And then you can show that when Q equals 4, you get to power SYK. When Q equals 2, you get a random massive fermionic quantum mechanics with a random mass matrix. But there's nothing stopping you from generalizing to Q. Here, for Q greater than 4, all Q greater than 4 theories are irrelevant. So it's hard to get SYK type physics. So then you'd say, well, what about bosons? Because a canonical boson in 2 dimensions has mass dimension 0, so you'd expect that any Q boson interaction in 2 dimensions would be relevant. Great, well that sounds promising, except when you actually try to write down such a model. Remember that what we're doing is we're writing down a model where the interactions are randomly sampled from some distribution where I can pick couplings that are positive or negative. So if you try to write down, let's say, some action for a boson that looks like this. So we'll take a canonical kinetic term for the boson, let's say phi I, plus J, let's make it Q boson interacting, Q interacting boson, so I1 through to IQ, phi I1 through phi IQ. But because these guys are randomly sampled from some Gaussian distribution where the coupling can be positive or negative, generically you'll have runaway directions and the theory is unstable. Okay? And in fact, I'll show you how we can show explicitly that the theory is unstable generically. So this is a generically unstable theory.
it means you don't flow to a fixed
Correct.
point.
Yeah. On the other hand, you could say, well, I could do something similar, and instead of taking q of these guys, I'll take half of the q of these guys and then square them. And then I'll construct a theory that has a positive definite potential. Let's say I prime, and this would be something like t2x. Last point. Suppose I take something like this. I1 to I2, phi I1, phi I2. That's great. Now my potential is positive definite. So the theory is not unstable anymore. However, what you will see, and I'll show this in the next talk, is that it doesn't flow to the correct infrared physics. So it turns out that constructing an analog of the SYK model in 2 dimensions is harder than you would think. Fermionic theories are generically have a generically marginal interaction at best, irrelevant if you're looking for Q greater than 4. And bosonic theories are either unstable or they don't flow to the correct infrared physics. And it turns out that the Goldilocks model is the one that we construct in our paper, which includes combining both of them into an n equals 1 supersymmetric CFT. I gave this talk in Japan last year, and I had to spend 20 minutes explaining what Goldilocks meant. So thankfully, I don't have to share. Anyway, thank you.
Any questions?
So indeed, the whole point was that we want to have a mass dimension 0, that was that corresponding. So indeed, if you now have superspace, then your superfield would have approximately have mass dimension 0, and then see what happens.
Yeah.
I take the bosonic model and integrate out randomness. I get something which looks very, very stable. Right? So what's your argument for stability?
You said a Gaussian?
Yeah,
Yes.
it's the same.
Well, so you have random matrix and then you diagonalize it and half the eigenvalues are positive and half negative.
No,
But for Q,
I just do the coefficients.
So that's the point. This is a field theory, so you start somewhere and then
Anyway,
you roll.
if you do the Gaussian integral, you get something which is very stable.
Not if you have a negative Gaussian. That's analytical dimensions.
The Gaussian is quadratic. It's very functional.
That doesn't converge.
No, it does. It's a Gaussian integral converges nicely. So good. And you get something which is very good. You get this connected term plus phi dot phi contracted to the power of 4.
Right.
Phi dot phi to the
Right,
power
right,
of 4 is very positive. Okay?
I see your point. I mean, you know, so for, if you take, for example, a randomizing model, or the Ising model with random bonds, then you get something very similar, except with you can map it to fermions and then do the integration of the random masses.
Yeah.
And then you pick up a
Square.
four body interaction. My argument would have been the same as David's, which is that you get, when you diagonalize half of some of them have negative eigenvalues. I don't know how to answer it in that context, but that's a good point. I mean,
The Hamiltonian with the negative masses.
So the theory is not unitary or something like that.
well, theory is not unitary, and I'll show this when we start computing correlators.
So Jeff, in 1 dimension, we were just doing quantum mechanics. That is the exponential growth of this correlator. If you go to 2 dimensions, you now have space and time. So are there more interesting sequences you could look at where it's growing also in space and as well as time?
So I think yes. We only look at the okay, yes. So yes, and you find that the growth is not the same in 0 plus 1 dimensions. In particular, the theory doesn't saturate the bound anymore. Possibly that's because it's growing in space and time.
Any more questions? So let's take Tina, so we'll resume at 11:05. Or no.
Got tea now, we're going to have the next talk, then we'll have tea.
Although I will need some time to raise the.
So that's okay, we'll take 2 minutes just to think of all of the tea after.